Bom dia a todo mundo. Vamos começar. So from this lecture on, maybe I put also for recording in. Anyway, from this lecture on, our main aim is to understand Hodge cycle for the Fermat variety. And in one email I wrote that really we will just assume some theorems, and once you assume these theorems, our study will basically be a linear algebra. Okay, so actually there x0d, and this is the projectivization of this one inside Pn plus 1. Oops, there is okay. And in the last 20 lectures, I a little bit made advertisement that we are going to capture the Hodge theory of this compact variety in the affine chart. So the affine chart will be x0 equal to 1. And so this x0 equal to 1. So it is the same as to say that 1 plus x1, maybe x1 plus d, x2 d, x n plus 1 d equal to minus 1. This inside Cn plus 1. And for some reasons, I will use parameter s here because I will consider this homogeneous polynomial equal to 1 also. So maybe just equal to s as some parameter. And actually, I will consider a more general affine variety generalizations of the Fermat M1. So the exponent will not be necessarily the same. Xn plus 1, Mn plus 1 equal to S. So this is in Cn plus 1. And mi's are natural numbers, all of them bigger than equal to 2. Okay, so one of the reason is that a lot of historical examples of some well-known varieties, they are in this format. And actually this. Let me write, let's call this one G. Let's call this G. And actually G is also homogeneous. It is homogeneous, but not homogeneous with the usual weight of variables, but in the ring, in the weighted ring, let's say Cx1, x2, xn plus 1. And you have to attach degree. In the usual context, degree or weight of xi is 1, but in this context it will not be 1. It will be m1 mi, lowest common multiple of m1 m2 mn plus 1. So this is the lowest common multiple of m1 m to mn plus 1. I will denote this one with d. Yeah. And when all the mi's are equal to d, then this is just again d divided by d, and then you will have the usual d. So this is we can consider this one as homogeneous polynomial if we put the weights on the variable. Okay, so so even so, my main example will be the classical Fermat variety. A lot of computation and affirmation will be for this general context. And maybe the reason for this, maybe consider this general context, maybe the most well-known example, this is elliptic curve. y2 plus x3 equal to, let's say, 1. Though in a dimension when n equal to 1, I will use, instead of x1, x2, I will use x and y, and this is an elliptic curve. Which is in the Weierstrass format, and so on. Soon we will we'll discuss some examples of this format. Anyway, so okay, so let me see. Maybe I share the screen a little bit. A window. Okay. From this lecture on, I will start to talk about chapter 15 and 16 of my own book. I will try to keep it in the same order that it is written. So let's pass the introduction. If you want to read the introduction. Okay, so let me. So first of all, about the homology, or the homology of my L. So maybe just in here I try to remember what we had. So remember that we had this classical n-dimensional simplex in Rn plus 1, and in one of the extra lectures by Felipe, then we defined a certain cycle. So let's define IMI, this set, and then let's define I, the product of all these I1, there is typo the I, this is IM1, IM2, and IMN plus 1. So let me see then. So this is IM1 and so on. And okay, so let's have some n plus 1 tuple containing just 0 and 1. So A is A1 until an plus 1. I think I have to write in the paper. Anyway, so we define this. So we take this beta from here, and we define this singular simplex in this way. So delta beta plus A in T is this one. So you see that here these are real numbers, T1 to the 1 over M1, and then there are this combination of roots of unity. So let's say that zeta. So this is zeta. Let's close. So you see these are the roots of unity. Anyway, it turns out that when we make this sum of all the simplices, because of all these signs, then the simplices they glue to each other to form homological cycles in maybe one typical. In dimension 2 is just division of the sphere into eight simplices. So we had already this one, and so we get elements in the H and L, and okay, from another. So now I will write that these are the generators of the homology. From another side, we have algebraic differential forms. For example, the algebraic differential form that I will oops, what happened? Something wrong happened. Okay, let's go again. So let's go. Okay. Okay. So from another side, we have let's say algebraic differential forms, and in this. So I have to introduce n forms. So for example, with some reason, these will be monomials, and then I will divide. I have made this combination. But anyway, so the idea is that we have a lot of algebraic differential form, and remember that by Atiyah-Hodge theorem at the end, the algebraic differential forms are enough to produce the Rham cohomology. So today, what I want to do first talk is the integration formula. So first, the observation before going to Hodge structure, Hodge cycles, and so on, that we have very explicit integration formulas. Maybe now I will try to explain. I will try to explain this integration formula. So we are integrating the n form over n cycle. Okay. So first of all, and this computation is the basis of all our computations for Fermat variety. So let me so first we have this beta factor. So let me say there is a rational number. Let's say this is the rational number, this beta factor, and there is some algebraic factor here. And so let's go to this beta factor. What is this beta factor? For this one, we need the gamma function. So first of all, we need this the gamma t. In our Hodge theory framework, we will have just the evaluation of gamma over rational numbers. So we will need this real t bigger than 0 such that this converge. in the comma in the complex domain it has analytic continuation and so on, but in this presentation of the gamma function, this is converted for real t bigger than 0. Gamma t, they do not appear directly in the let's say in Hodge theory or as periods, but what is more common is this beta function, beta IB integral 1 over 2 0 s to the a minus 1 1 as s b to minus 1 ds. And it turns out that this beta function you can compute in terms of gamma function, and this is the gamma a gamma b divided by gamma I plus b. Again, for the convergence issues, we need this real a and real b bigger than 0. And remember that at the end, we will just need the case a, b positive rational numbers. Okay. And okay, so there is another formula. This actually, we will need this one. This is the multivariate, multi-parameter version of beta function. So beta a1 an plus 1, it will be the integration of t1 to the a1 minus 1 blah 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 dt1 dtn. So that we have removed dtn plus 1, and then delta n. Delta n was this classical n simplex inside r on plus 1. Okay, so this is the beta function. Again, we can prove that it is equal to this one. Okay, so let's return back to the simple proposition that I was talking. Anyway, I am now integrating this differential form over the topological cycle delta beta. So it will be this irrational number, this beta number. And a priori, you see that this beta we don't know. In principle, it might be a transcendental number. And because in general, the periods are transcendental numbers, and this algebraic number. So let's see. Maybe just to so the point is that, so I have indexed the topological cycle by beta and the differential form by beta prime. You see that the possibly transcendental number of the integral depends just on the integrand and not the domain of integration. So that just the algebraic number here depends on the delta beta, which is the domain of integration. And if you go through the proof, I mean, this is just a simple calculus proof. For the first time when I was writing the book, I gave this as exercise to Roberto, and I mean, and in the first version of the course, and I mean, you have to just start integrating, and so you see that you just start integrating the omega beta over one simplex, and then okay, then just substitution, and then when you put the parametrization of your simplexes, then this algebraic things will pop up, and then there will be integration in the real part, and then you will get the formula. So it is not hard to get this formula. Anyway, the moral of the story is that before going to too much Hodge theory and Hodge filtration stuff, we have explicit formula for integrals in the case of Fermat variety. Okay, so Okay, so now let me stop sharing and go again to up. Okay, let's come on. Okay. Okay, so let's back to to the camera. So first of all, okay, so delta beta in this I. So this is a kind of we got some idea of the proof of this one when we were doing the topology, but at the end is a basis of Hn. So this is one of the things that we are going to assume. We have really this sky is freely generated, and we have actually a basis. And from another point of view, the second theorem also that we have to assume this omega beta that I wrote, the same set form a basis of Hn the Rham. So anyway, we have a basis of the homology, we have the basis of the cohomology, and remember that again this omega beta was this x beta, how it was, then there was up to some rational number, it was in fact I have used also the notation eta beta, and eta is xi dxi, and well, there is this minus 1 to the I, and then division by 1 over mi. Anyway, we have a basis, and the proposition that I showed you, we know also the integration of this guy over this guy. Okay, so let's go further. So in order to understand the Hodge conjecture, we need to talk about Hodge filtration and so on. Maybe right now I will try to explain this one. So beta in I, remember that I was, what was I? I was, let's keep the notation I2, In plus 1, I, or IMI, doesn't matter, 0, 1, Mi minus 2. So so this notation, I will use this notation A beta. A beta is this rational number, beta I plus 1 Mi, I equals 1 n plus 1. And that actually it turns out that this A beta is responsible for distinguishing the differential forms in the de Rham cohomology, because Hodge filtration is a kind of distinguishing differential form from each other. So I am going to talk about the Hodge filtration that I told last time. Maybe I am going to repeat it. Let's say this section 15.3. But since I'm going to repeat it in this general context of MI, that I didn't do it during the course. Anyway, first of all, is you will see that this A beta are between n plus 1 and 0. And this is because the maximum of mi is mi, let's say, at mi minus 1, and then all of these guys are strictly less than 1, so it will be less than n plus 1. So let's between 0 and n plus 1, I have 1, 2, n. Okay. Okay, so I will use Wn. So Wn will be those omega beta, such that I beta. This means it's generated by, they are not integers. This is, let's write them as n h theorem l l. So first of all, I explain what is this computation we did last time. So hn theorem. Again, now the discussion that I am going to tell, actually I have to take m1, m2, mn plus 1 equal to d, maybe because there is this issue at infinity. Anyway, we have this L, and so L was inside the Fermat variety of dimension n degree d, but for its compactification we need Fermat variety of dimension n minus 1 and degree d. So let me try to. So anyway, this is xn xdn minus 1 given by x0 equal to x0 equal to 0, which at the end it is the projectivization of x1d plus xn plus 1d equal to 0 inside Pn. Anyway, what I am saying that my Fermat variety, the compact one, is the union of this affine variety with a Fermat variety of one dimension less at infinity. Okay, so I will use this notation that I will use x for this one, and the variety at infinity I will use as y. So this part of the Rham cohomology of affine variety has to, they are elements which come from the compact one. So let me say hn the Rham x. So we have the restriction map. This is the restriction map, and its image of the restriction map is exactly this Wn. So this means that when I am in the affine part, affine chart L, I know exactly which differential forms from the compact one, those omega beta, such that a beta is not an integer. This W has to do with this weight filtration, because one of the great let's say discoveries of Deligne was that at the end any variety carries Hodge filtration and weight filtration. In our case, we are dealing with affine variety, and this is just notation that I have borrowed from this context. Anyway, one thing that then we are going to assume, apart from the statement that I told, omega beta such that beta is not integer. They are actually they are the image of the the compact elements of the compact Fermat variety. Okay, so let's go to the next one. So there is no this so Wn itself. So now is divided part of Wn such that beta is strictly between 0 and 1, beta between 2 and 1, and so on. And actually this way of distinguishing differential forms will give me the Hodge filtration. So the statement that we are going to use, so maybe one statement that, that I am going to assume, one. Another statement that I am going to assume at the end. Maybe there's let me write down the restriction map. Hn the Rham Hn the Rham x Hn the Rham L. So I said that okay, its image is Wn. And remember that here we had I tell that we have Hodge filtration. So the idea is that even if you start the course from this lecture on, whatever I am saying, you can put it as the definition of the Hodge filtration that we are going to use. Fn plus 1 equal to 0. So image of Fi, let's say it is given by it is given by omega beta. First of all, a beta is not supposed to be integer. Well, omega beta is always positive, and also beta is less than n plus 1 minus I. So the moral of the story is that omega beta such that a beta is not integer and a beta is less than n plus 1 minus I. This will be giving me the Hodge filtration. So whatever how Hodge filtration is, this means that this kind of differential form are very special differential form. And okay, so the idea is that to just make some assumption from the first 20 lectures. So what I am saying at the end, the Hodge cycle in our context, what it will be. So first of all, we will be interested. So first, let us write in the compact context, and then I will make the translation into. So it will be a cycle such that integral omega beta delta equal to 0. So for which one? Remember that they must be in Fn plus 1. So translated this one to F beta not integer, and then beta is less than n plus 1 minus n half plus 1, which will be n half. Anyway, so if you have not followed the course so far, so then you will assume this one as the definition of the Hodge cycle. So maybe I put this picture again. So for Hodge cycle, n must be even. 1, 2. So we have this n half in the middle. And also n half plus 1. So for all differential, for all beta in this part, this is this n half and n half plus 1 is this is the middle piece, exactly the middle of the interval between 0 and n plus 1. So one box before the middle, then we have beta, let's say beta less than n half. So then this is the Hodge, the definition of the Hodge cycle. And so remember that delta betas form a basis. So this means that at the end I have, if by some reason I say that okay, I am interested just on cycles with support in L, at the end I can do this one, and it will turn out that really the homology of the compact X is most of it is it's just in L. Then I can say I can start writing my n alpha and beta in terms of this delta beta that I had, and I have explicit integration formula. And so at the end, it will turns out that I can one can write start computing the Hodge cycles. And this is the thing that we will try to a little bit understand. Anyway, so let me maybe I will tell you something about. Okay. Something about this passage from the X to L, or maybe let me. Okay, let me see. Okay, maybe something that at the end maybe I show you today. From now on, the idea is that start doing computation. So in the next 20 minutes, I will show you the codes that I have written to deal with these Hodge cycles of the Fermat variety. Okay, so far any question? Let me see. Okay, let's try to go to one example, or maybe this. Okay, well, and at the end of the maybe I tell a few words about taking a support in L. H and L Z. We have inclusion in H and X Z. And remember that here there was relative cohomology, and then by taking the corresponding Gaussian sequence, this is Hn minus 2 y z, and here the Hn plus 1, Hn minus 1, Hn minus 1 y Z. Okay, so by Lefschetz, well, so remember that dimension of y. Y is the Fermat variety of dimension n minus 1. By Lefschetz theorem, this is Z. So so if you are interested in a Hodge cycle here, let's say, and this map was what? This is an intersection map. This is the intersection map, and this is isomorphic to Z by Lefschetz theorem. So anyway, you see that up to this one dimension, anyway, most of the cycles here are supported here, and later we will be back to this issue. So anyway, taking the support of cycles here, here it doesn't, it's not so much problematic. And another things, maybe before going to the computation, I have to tell. There are these beta integers also. This one we will not use it, but let me a little bit tell about this one. Y, x. This is my y. This is my x, and omega beta. Beta integer. So let's say omega beta in natural number. So have let's say residues around y equal to 0. And actually, these guys have to do with the cohomology of y, in the sense that Hn deron L. So let's write down the Hn deron x, and here it goes to Hn minus 1 deron, the same guidance sequence in cohomology. What I told you at the end of the day, this goes to Wn, but the differential forms here with a beta integers, they are those which gives elements here, and this is the residue of these differential forms. I will not use this differential form because at the end I am interested to a little bit play with these Hodge cycles of X itself, but for some discussions it might be useful in the future. Anyway, let me try to share some. So a lot of things that in this chapter you see, they are implemented in singular, and maybe it would be nice to get used to computation with singular. So okay, let me see what I'm going to do. Okay, so I will just show you a little bit the codes that I have written. Show present now a window. Okay. Okay, so first of all, let me see. I forgot. Anyway, there is maybe just a moment. Your entire screen. Okay. Okay. So first, mathematical evaluation, computer codes. Then, so a lot of computation that we are going to a little bit handle here. They are. I have written codes in this foliation fib. So if you have to just install singular and also this foliation point lib in your in a directory, and you have to start using it. And okay, so let me. Okay, so let me. Now I am trying to do one example, but this one example with the computer, because at some point the computation will be out of hand computation, so we cannot do by hand, so we have to do it anyway by computer. So the idea is that you get used to this okay, so let's singular. Okay, so what I need. So the first we need to to download my library, this foliation point lib. So I started from my directory that I had put this foliation lib. So let's start. So this is, let's say, so what is this? So now maybe I go to the, so let's for a moment go to the camera again. So I am sharing, but you can pin on the camera. So the idea is that I want to show this computation that I will start doing with this x1 to the 4 plus x2 to the 4 plus x3 to the 4 minus 1. Oh, sorry. And so this will be so this exponents 4 4 4 are these m lists that I put there. Okay, so let's go again. Let's go again to the code.
So Hossein, just what exactly do you want to compute?
No, I want to show how to get this basis of the Rham cohomology and delta betas, and also the implementation of these integrals.
Okay.
Because later we will need these all these codes. This is just getting used to this code because later we will use it. Okay,
right.
Maybe so. Let's say maybe I just so this is the n. N will be the dimension, because at the end I will use this now let's say the D matrix. Just this D matrix. D is in our case is y is 4. So I will need a weighted ring for my purpose, because remember that I told that even this generalized Fermat variety is homogeneous. So this is just to fix the ring. So I have defined a ring with rational coefficients. I will need a parameter z. This will be the root of unity. So it has the variable x1, x2, x3, and so maybe I will need that this parameter z is a root of unity, because remember that in maybe I just okay. So anyway, that's it. Base ring. So I need you see I need in this context, z will be the fourth root of unity, which is the complex number I. So you see that I need the coefficients, rational coefficients with parameter z. Z will be the fourth root of unity. Variable x1, x2, x3 for computing one. The singular must have an ordering of the variable and so on. But for the moment, we don't care about this one. Okay, so let's so mixed Hodge Fermat exactly has to do with this distinguishing the differential forms that I told you. I think maybe I do this one. Okay, so LL. So over a list. So this list contains of two lists. So the first list. This is exactly those are beta between 0 and 1. And then this is this, so it is just one element. And this we have now how many elements? 19 elements that are beta is between 1 and 2. And at the end there is again one beta such that beta is between 1 and between 1 and 2. So these are. We are not doing computation, but what I'm saying that I will need these codes in order to proceed with the course, because the linear algebra that we will get from Hodge theory of Fermat, it's a kind of linear algebra. It's most of it, it's impossible to do the computation by hand. Anyway, so this means that maybe the first part of the list is the one that I explained. It has also the second part, lead to, and this has to do with the differential form with r beta as integer. These are exactly r beta 1, and this is r beta equal to 2. And I said that I will, for the moment, we will not use differential form, but they have to do with the Fermat variety ad infinity, which has one dimension less. It has other this command also has other output, but slowly we can we will use it. But for the moment, I don't need it. Okay, so maybe for example, let me just define my my polynomial f. So this is just for. So well, this homogeneous polynomial f x1 to the 4, x to the 4, and so on. So with this command k base, I have to take a basis of the Milnor vector space. Remember, let me do this one. So this is this 27 elements that you are seeing here. They are just the elements of the Milnor vector space. That at the end, from that one also we constructed the monomials for the de Rham cohomology. Maybe another comment that at the end we will need it. Okay. So first of all, okay. So I have to make to do computation. I have to identify my delta beta also with these monomials. So during the rest of the course, I will identify delta betas with this differential this monomials also. Maybe let's go back to the camera just a moment. So artificial identification. I mean, this is just to keep in mind that how to say that I want to handle also delta betas in by commutative algebra and stuff. So I will just identify this x beta, and remember that C V, let's say Vg. So let's call this one G without one G. Vg is Cx Jacob of G, and this is generated by x to the beta, all such that all beta i's at the end between 0 and mi minus 2. And oops, there is a camera issue. Okay, so maybe one thing is also maybe start showing that we can start integrating differential forms over our cycles. So in some sense, let me write the so this list IL that you see here at the this list IL, these 27 elements that you see here, at the end they will, in the same time, they will represent for me the differential forms and also the cycle delta beta. So let's so I can start integrating so this command period matrix ILZ. So the first IL are the list of even I forget it, but let's see. So hell period matrix. Oh no, this will not work. Example. Period. I have. Okay. Okay, so let me bring it again back here. So the command that you see here, this period matrix, maybe that I don't write that as print. So the first IL is represented as cycles, and the second IL representative differential forms. And you see that you will get 27 times 27 matrix. These are, each entry is the algebraic part, not the beta factor part. We will see that for the definition of the Hodge cycle, this transcendental part will not affect our story. So you will get this 27 times 27 matrix in what? This is in Z, which is the fourth root of this is let's say the fourth root of unity. Anyway, and here you have to give this parameter Z, which is the fourth root of unity. Anyway, what I wanted to say from now on, in order to a little bit play with the Hodge cycles, we will need these codes. And let me stop here. So before going to talk about algebraic cycles, so the first thing that we are going to do a little bit play with the Hodge cycles themselves. And at the end, the definition of Hodge cycles in this case, after computing the periods it is explicit. It's an explicit equality. So this means that even we can find the base of Hodge cycles and so on. Okay, any question?
Hossein, I didn't really understand why did you make this identification of delta betas and the monomials? Like, is it just for computing, or is there a more sophisticated idea?
No. It is just for to be able to handle the delta beta in the computer. It is just for this one. Anyway, what I am saying that I need to store the integral inside the computer. No, I have to say these numbers: integration of omega beta prime divided by delta beta, and I have to form a 27 by 27 matrix, and I have to say that the columns and rows of this matrix are indexed by what? In the book, in the theoretical term, the rows are indexed by delta beta and the columns by omega beta prime. No, and but in order to make it understandable to computer, I would say that the both rows and columns are identified by these monomials, omega x beta. It is just a maybe let it is moment again. Anyway, what I'm saying, actually not this identification. Delta beta can be identified with beta itself. Beta is in this set. Beta is in this I1, I2, and so on. And at the end, this x beta also can be identified with this set. And I don't want to handle this set. Well, the singular is a program for commutative algebra. So at the end, one handles a lot of monomials, polynomials, and so on. At the end, I identify I1 this I set with delta beta, with different the Rham cohomology, everything with this basis of monomials. And this is just for to be able to work with the computer to do the computation. It's not something deep.
Okay.
Maybe I stop recording and then we can talk more. Just a moment.